Welcome back. Today we're talking about isomorphisms. So recall that homomorphisms are relationships or transformations between vector spaces that exhibit linearity, that is, they preserve linear combinations in the domain in the codomain. So if I have a linear combination of vectors in the codomain, say c1 times the vector v1 plus c2 times the vector v2, and then I apply the transformation h to that, then that's going to evaluate to a linear combination of the images of each of these vectors individually. And this was the only rule that we had for homomorphisms. As for the dimension of their spaces, we didn't really have any constraints about that. Let's say this represents the domain, which I'll call V, and maybe V has dimension 4, for example. And this is the codomain, and we'll call that W as we have been. And so our transformation H takes vectors from V and puts them in W. Maybe the codomain W is larger than the domain. Maybe it has dimension 5. And even more than that, maybe the image of the domain in the codomain, which is the range, evaluates to an even smaller space within the codomain. Maybe the range of this transformation, or the range space, only has dimension 3. So we can see that the dimension of these spaces can still be out of sync when we're talking about homomorphisms. Homomorphisms already describe a similarity between vector spaces, namely that if two vectors are related by homomorphism, that is, a vector in the domain evaluates by that homomorphism to a vector in the codomain, then they will behave the same way in their respective vector spaces. But if I wanted to come up with a concept for a stronger relationship, a stronger degree of similarity between two vector spaces, V and W, I could come up with a new condition, not just the condition of linearity, that linear combinations in the domain are preserved in the codomain, which is this one right here, but our new relationship between vector spaces will also have a new condition, that the transformation is a bijection. And as I will prove later in the video, that means that the range space in the codomain will have the same dimension, and that the dimension of the codomain and range space will be the same as the domain. So if V had a dimension of 4, then W and R of H, which would be the same thing, would both also have a dimension of 4. And this leads us to the main definition of this video, which is an isomorphism. It's like a homomorphism, but specifically it is a bijective homomorphism. This means that it abides by two conditions. The first one is linearity, again, that if I have a linear combination of vectors in the domain, say c1 times v1 plus c2 times v2, and then I apply the map h to that, that's the same thing as c1 times h of v1 plus c2 times h of v2. The second condition is that it is a bijection. And a bijection, as I detailed a few videos ago, is a map between two spaces that is one-to-one and onto. It's injective and surjective. One-to-one means that if A equals B, then H of A equals H of B. In other words, if two elements are the same in the domain, then they must evaluate to the same thing in the codomain. I cannot have two elements in the domain that are different evaluate to the same thing. And if they evaluate to the same thing, then they are the same. And onto means that for every vector W in the codomain, there exists some vector V in the domain such that H of V equals W. In other words, every vector in the domain is mapped to by at least one vector in the domain. If a map is one-to-one, preimages of elements of the codomain can contain at most one element of the domain, and if maps are onto, then preimages of elements of the codomain contain at least one element of the domain. And so, if a map is a bijection, preimage sets contain exactly one vector from the domain. One vector of the domain is mapped to or associated with one vector of the codomain. There's a perfect correspondence. And if V and W are related by an isomorphism, say F, then we say that V is isomorphic to W, or V isomorphic to W with this symbol. Let's start out with a relatively simple example. R3 is isomorphic to P2, the space of quadratic polynomials, under the following isomorphism F. F takes a vector in R3, a, b, c, to the quadratic polynomial a plus bx plus cx squared. I believe I actually used the example of R3 being similar to P2 in a recent video, and I mentioned how in R3 we have the x, y, and z directions, and similarly, although we never represent P2 graphically, you could almost imagine P2 as having a constant, linear, and quadratic direction. And so in that way you can imagine that R3 and P2 are very similar. This transformation basically just associates the corresponding components of a vector in R3 with a quadratic polynomial. They each have 3 degrees of freedom in the way their elements can vary. Nonetheless, let's verify that this is an isomorphism. So again, an isomorphism is a bijective homomorphism. It's a homomorphism that is one-to-one and onto. So the first thing we'll do is verify that it's a homomorphism. So a homomorphism preserves linear combinations. So if I apply the map F to a linear combination of vectors in the domain, say S1 times A1, B1, C1, plus S2 times A2, B2, C2, then that should be the same thing as S1 times F applied to the first vector plus S2 times F applied to the second vector. This vector on the inside can be simplified to S1A1 plus S2A2, S1B1 plus S2B2, S1C1 plus S2C2. If I actually apply the map F to this, the first component of this vector becomes the constant term, the second component of this vector multiplies x, it's the linear term, and the third component of this vector multiplies x squared, it's the quadratic term, just like this. Hopefully you can see that this polynomial is really the same thing as S1 times the polynomial A1 plus B1 x plus C1 x squared plus S2 times the polynomial A2 plus B2 x plus C2 x squared. But this first polynomial in parentheses is exactly f applied to the vector a1, b1, c1, and this polynomial in parentheses is exactly f applied to the vector a2, b2, c2. And so our result is s1 times f applied to the first vector plus s2 times f applied to the second vector. F demonstrates linearity, therefore it is a homomorphism. The next thing we must verify is that f is a bijection. We'll start with verifying that it's one-to-one. If f is one-to-one, then it means that if two outputs are the same for two different inputs, it implies that those two inputs are the same. And so notice that if these two outputs, which are these quadratic polynomials, are the same, then that means that they have the same constant terms, so a1 equals a2, they have the same linear terms, so b1 equals b2, and they have the same quadratic terms, so c1 equals c2. The components of the vectors, the inputs, a1, b1, c1, and a2, b2, c2, that's the other vector, are the same. Two vectors are the same if their components are the same. Now, if f is onto, it means that every element of the codomain, which in this case is p2, is mapped to by at least one vector in the domain. And it should be even more obvious that this is onto because any element of the codomain, say L plus mx plus nx squared in p2, is of course mapped to by the vector in R3, L, m, n. So it's one-to-one, it's onto, therefore it's a bijection, and we also verified that it's homomorphism, so we can confidently say that it is an isomorphism. Specifically, that R3 is isomorphic to P2. These vector spaces are quite similar. Here's another, perhaps less obvious example of an isomorphism. So this is an isomorphism G that also goes from R3 to P2, and it has the following action. If I input a vector from R3 ABC, the result that I get is C plus the quantity A plus B times X plus the quantity B minus C times X squared. So whatever A, B, and C multiply in our result are going to be each of the three directions or the 3 degrees of freedom within P2 that we have in order to span the entire codomain. Again, this is an isomorphism, which means, as I will prove later, that the range space and the codomain have the same dimension and that that dimension is the same as the domain. So naturally, the range space, which consists of all of these output vectors here, has to span the entire codomain, and since P2 is a 3-dimensional space, the range space has to be 3-dimensional, therefore we need 3 degrees of freedom. C, A, and B will multiply each of those 3 degrees of freedom. So let's simplify this in the following way. C is the constant term, but we also have C in this x squared term. And if we expand this x squared term and similarly expand the linear term, we get C plus AX plus BX plus BX squared minus CX squared. And then if we simplify this, we get A times X plus B times the quantity X plus X squared plus C times the quantity 1 minus X squared. So X plus X squared, and 1 minus X squared represent those 3 directions. Throughout our proof that G is an isomorphism, it will be more useful to consider this as the output rather than our initial output. Again, for the first step, we verify that G is a homomorphism, meaning that it preserves linear combinations from the domain in the codomain. In other words, G applied to, again, S1 times A1, B1, C1 plus S2, A2, B2, C2 should be the same thing as S1 times G applied to the first vector plus S2 times G applied to the second vector. As we did in the last example, we can simplify the input on the inside to S1A1 plus S2A2, and we can do the same thing for the second and third components as follows, like this. And then when I evaluate it, I get the following result, multiplying x plus x squared, and 1 minus x squared, where, for example, S1C1 plus S2C2 is treated as C in the original transformation, which is exactly S1 times the polynomial A1 times x plus B1 times the quantity x plus x squared plus C1 times the quantity 1 minus x squared plus S2 times the same polynomial but where A1 becomes A2, etc. And of course, that's exactly S1 times G applied to the vector A1, B1, C1. And the second polynomial is just G applied to A2, B2, C2. This is a homomorphism. It preserves linear combinations. The second thing we have to prove is that G is a bijection, meaning that it's one-to-one and onto. So let's again start with one-to-one. So if G applied to two different input vectors, a1, b1, c1, and a2, b2, c2 is the same thing, a1x plus b1 x plus x squared plus c1 1 minus x squared, and a2x plus b2 x plus x squared plus c2 times 1 minus x squared are the same thing. That can only be true if their coefficients are the same. Then the components of those vectors are the same. So we've shown that if two different vectors evaluate to the same output, then that means that the vectors themselves, the inputs, have to be the same. Next, we show that G is onto. This is when it becomes really important that we rewrite the output as a times x plus b times x plus x squared plus c times 1 minus x squared instead of what it originally was. We see just 1a, 1b, and 1c multiplying the different parts of this polynomial. And then we can determine that if we have some polynomial output, lx plus m x plus x squared plus n 1 minus x squared, then it must be mapped to, by the vector in R3, lmn. So G is one-to-one, G is onto, G is a bijection. It's also a homomorphism, therefore it's an isomorphism. We could also have an isomorphism from a space onto itself. So if I have this example, f, which goes from R3 to R3, and the input is all the vectors in R3 x, y, z, therefore a three-dimensional domain, then the output also has to be three-dimensional. And if the codomain is R3, that means my inputs are all the vectors that fill R3, and my outputs are also all the vectors that fill R3. It's just that vectors from the domain R3 are associated with different vectors in the codomain R3. Take the action of f, for example. When I input x, y, z, I get 2y, negative 2x, and 2z. Perhaps you can tell that the action of this map is scaling all the vectors in R3 by a factor of 2, and then rotating them clockwise 90 degrees on the xy plane. So again, just for the sake of visualizing things, if this black vector is the input vector, then its output, which is also going to be a vector in R3, is going to be scaled up by a factor of 2, so it's going to get twice as long. It's going to go from the origin to this endpoint right here. It's going to be this red vector, and then let's say it projects down onto this point on the xy plane. It's also going to be rotated clockwise by 90 degrees on the xy plane. So it's going to end up over this point. This is a 90-degree counterclockwise shift. It was scaled up by a factor of 2 and then rotated clockwise by 90 degrees on the xy plane. So instead of thinking of taking them out of one vector space and putting them in another vector space, we think of moving them around within the same vector space. We're just changing the vectors within R3 the whole time. This kind of isomorphism from a space onto itself is called an automorphism.